didn't really care about it being clever. It had to be good enough and work as quickly as possible. So TCP/IP basically shot token ring in the head, took it outside and shot it. Shows over, end of story. TCP was good enough to make it work. But because it is good enough, it does not make some mess ups. And this is how to cope with this and work it out somewhere. So if I'm sending a conversation from one machine, which might be downloaded in a large film, for example, or it might be a VoIP conversation, literally talking across the phone from one place to another. We need some way to make certain the conversation has started, all the bits are in the right order, and at the end it finishes again. Because if we don't tell it we're going to finish at the end, it's going to sit there waiting for more stuff to come down. And, well, you know, how long am I going to wait? You know, what's the point of this? What am I going for? Right. Call them slide-in windows. Our problem or solution is that we've got a piece of traffic going from A to B, which could be a VoIP conversation on an FTP file or something like this. An awful lot of chunks, different sets of packets. We've got to try and work out, okay, first of all, to take them and reassemble them to get a useful looking file or a voice conversation that makes sense. And secondly, got to know when the conversation has ended. So we don't sit there at the end of the conversation going, oh, has it finished? Has it finished? Has it finished? Has it finished? There must be a clear ending of the thing. Okay, this conversation, this transmission is finished, end of story, we can free up our resources and do something else at the same time. So up here, we're checking, okay, a session being A, download of a file, A, talking over VoIP, A, watching of a streaming film, something like this. That's that. Look, the presentation is probably the woolliest one when it comes to TCP/IP, because these days most machines, including Apple's and Linux machines and Windows machines, present things much the same way. So you've got your thing, it sees zeros and ones, and it makes out of it a text document, or it makes out of it a sound file or whatever. And it tends to use similar sorts of stuff. So over the years, it's been common to use Unicode to encode words. It's been common to use certain other codes to encode video or sound or whatever you want to do with it. If you went back many different years, many machines were just quite different. So you get an IBM server machine compared to somebody else's server machine, and they were just so different. The way it handled what was a number or what was a letter might be quite different. It would be each individual machine taking the stuff and then making it into proper words and so forth. But the presentation layer, although important, it's almost certainly the same on most machines. It's take a Unicode set of numbers and make out that set of numbers a word. That's what I'm talking. Back to application, we go back into the common sense part of it. The application is the thing that's actually doing something. It is the code inside a web page. It is the file contents of the FTP file. That sort of plot coming down like this. So right in the very middle, after the transport stuff, towards the end of this, we've got our actual thing that's going to be our web page or whatever. And it may seem, well, we've got all this data link information and network information and ports information and session information, maybe presentation, maybe not. Then the application layer at the top, that's an awful lot of stuff. But in reality, these are only a few bytes long, you know, a byte or two, which leaves hundreds of bytes for the stuff in the application. So in effect, out of scale, there's plenty of space for the actual stuff in the middle over there. Amongst one key part that relates to TCP/IP is when I'm sending stuff up, somewhere around this layer, I'll put it by transport, we've got a choice. We can do UDP or TCP. For those who want to know, use a datagram protocol, transmission control protocol, but it's just written UDP or TCP. It also links to the use of ports over there. I can send things two ways using the TCP/IP stack. Either I can just blat it down there and not give a monkeys. That's UDP. We think of UDP like sending a postcard from A to B. We put the stuff on the postcard, pop the postcard in the letterbox, and damn, job's done, out of here. Maybe the postcard arrives, maybe it doesn't. If it doesn't, then Auntie Joe didn't know you had 2 weeks fine in roads, but it's not the end of the world, is it? And TCP/IP, the TCP plot, is there's some sort of error check. It's like pick up the phone and say, hello Auntie Joe, can you hear me? Yes, says Auntie Joe. Oh, we're having a lovely time in Rhodes, Auntie Joe. Oh, thank you, little Billy. And moves on like this. So there's a degree of talking backwards and forwards. I've received this message. Thank you. Send me some more stuff. And this works at TCP/IP with its sliding windows. Down come these packets. And then the one at the other end, the receiver says, yeah, I've got that. You're fine. So something comes along. And then the receiver sends stuff back. And there's like a gap in it. So it's not always acknowledging the same order it's receiving, but it all works out okay. So it might receive number 7 and acknowledge number 1, but it works fine like this. Then if the receiver doesn't receive stuff, then it gives up listening. If the transmitter doesn't receive the acknowledgements, it sends it again, but not forever. It doesn't think, okay, nobody's got this, I'll shout louder and longer and more and more and more. It will after a point think, well, I'll give up on this. Fool's game this, so it just stops sending it. So you end up with an endless loop. If we've got this TCP plot over here, we don't just keep sending stuff again and again and again. They send stuff, wait for a reply, send stuff, wait for a reply, send stuff, wait for a reply. And if no replies come after a certain length of time, it gives up, ends the conversation, just moves on gracefully and just get the heck on with it. So you don't have a loop waiting for things. The UDP works nicely for concepts where we're not really that bothered. If you're watching the typical ones of a YouTube video, you're watching your streaming video on YouTube or iPlayer or something like this, and down it comes and the guy or lady does their stuff and so forth. And if you miss a bit, you miss a bit. So if I suddenly jumped and it all went out of sequence, but you catch up in a bit, nobody really minds, do you? If occasionally the sound squeals a bit, then it's not, you can work it out and fill in the gaps in your brain, you're okay. UDP's okay for like that, so we just want to get it good enough, get it down there and not worry about it. But if we use the complete checking of TCP on like a video download, or we're watching online, if a section wasn't received, what would basically happen is that the receiver would ask to send it again, so it would go in a loop and it would go back and restart and go back and restart, which will work, but you're not that bothered. You just want to watch the darn thing and get the heck out of Dodge, don't you? So UDP works better for that. But when we're considering things, we can send stuff in traffic as UDP or TCP/IP. And most, well, I don't know most or not, the stuff you generally use your web for, your HTTP, your FTP stuff, email, it's going to be sent TCP/IP. But things that are just fairly throwaway, fairly harmless stuff are going to be sent UDP.